Let's take a look now inside the system unit. That's that box that the keyboard connects to. We can talk about memory as semiconductor memory. That just stores on-off patterns, but how does a computer manipulate these? What it comes down to is electrical gates. Gates that can make decisions based on electrical charges being present at one or more incoming conductors or wires. An AND gate, for example, will generate an electrical charge here only if both of these have an electrical charge on them. So if A and B, let's say, are true because they have an electrical charge, then C will be true also. In this case, an OR gate, a charge here, or both places, would produce a charge here. The little zero symbol or the circle symbol negates things. A NAND gate, negative AND gate, will generate a signal only if there's no charge present on both of these. You see, that circle related to this sort of a symbol negates things. So this does exactly the opposite coming out as it got in. These circuits can be used to express Boolean algebra. Now, we're not going to delve very deeply into this. I only wanted you to know that these sorts of little basic components, logic components, existed, and they could be implemented in electronic form. When implemented that way, it becomes possible to build up logic circuits using just these very tiny simple components. And this is the way that that's done. So using those symbols for those gates, an engineer or a mathematician can come up with a combination of gates that produces a desired set of output signals for given inputs. This can be built up into circuits that then produce signals that we can interpret as modified information. Here's the way it usually works. A computer has a clock that pulses every fraction of a second. During the fraction of a second between pulses, this time state, certain signals might appear and certain outputs might appear. In the next clock pulse, the signals here may change, having been driven by other gates, and now a different set of signals appears and a different set of outputs. So the clock pulse dictates the speed of the computer, and when you see something like a chip that's rated at 1.6 gigahertz, we're talking about 1.6 billion cycles per second. That is, these changes in the signals. So the higher the clock rate, the higher the speed of the CPU, the faster this sequence of changing signals can be processed. And what happens is these signals represent altered information. The outputs here go into other gates, and very large collections of gates form units of electronic circuitry that can actually make decisions based on information content or on bits that are representing program actions. That is, actions that we want the computer to take, really a program expressed in this binary way. Here's another way that gates are sometimes combined into larger circuits. The gates by themselves don't do very useful things. They're very, very tiny components, but when placed together in circuits like this that are designed to accomplish logic, a given set of inputs can cause a vast array of outputs to be generated because of the action of the gates. More and more can be combined to form various circuits that add binary numbers, or subtract or multiply or divide, or move information from one place to another, driven at the rate of change of the clock pulse, the oscillator in the computer that's generating these pulses at a very rapid rate that sort of times the operation of the entire computer. On this diagram, as opposed to this one, here we have a piece of a representation of logic gates arranged into some sort of a processing array. Everything that you see in the prior page is contained in a little box like this. In other words, the entire circuit, of which this is just one small part, is contained in a box represented on this diagram here. And other circuits like that are combined in such a way that this represents the schematic for an entire computer circuit in a chip. These are the wires in and out of the chip, and the whole chip is just a small thing about the size of your fingernail. Those chips and much more complex chips might look like this. This is actually a photograph at a very small scale of one chip that would be probably about the size of a pencil eraser, certainly not much larger than that. They're grown on a wafer of silicon like this that's processed with various chemicals and various kinds of photographic materials called a resist, that is some sort of a coating that resists the etching of acid, leaving certain areas exposed so they can be etched, and multiple layers built up on this sort of a slice of silicon here. You see multiple chips are manufactured, and around the edges, chips that are not useful, parts of them are manufactured because the size of these wafers varies slightly. It's the chips here that are grown this way that look like this, having been designed with very, very large diagrams that are then photographed and photographically reduced to produce the kinds of images you see here. So here's a person's hand. You can see this is a few inches in diameter. On it are all of these chips. They're later cut apart, and these are the connection points to which wires are attached to the connectors on the case, usually little gold wires. All of these things really are transistors and other circuit elements that have been grown, wired together to form this circuit. Very complex. This might contain millions of transistors arranged in all sorts of different circuits, designed to be fed by signals coming in on these connectors, which join into various parts of the circuitry. This is what makes modern computers possible. These are very complex, very tiny circuit components that form the heart of a computer. And so many devices these days have them in any kind of information stored electronically. At the heart has exactly this type of circuitry. Physical view of a chip, which you just saw on the prior page as one of these cut out complete chips, would be mounted on some sort of piece of plastic or ceramic metal like this that results in these leads that can be placed into a socket being connected to those connection points around the periphery of the chip. The chip itself would be small like this. Here's a pair of glasses and a dollar bill. Sitting on it, these might be memory chips. Larger squares of this material might house the kind of a chip that is the central processing unit. And the reason that that sort of a chip is bigger than this is that there has to be enough room around the edges for the greater number of wires coming in to connect to the circuit. The circuit itself would still be small, probably about as small as this little number 1 here, but the case is big because all the wires that have to be physically connected to the connection points on it. And here's the way a chip might be represented in a diagram showing external components hooked up to it. This would be mounted on a motherboard, and these external components are electronic components that are also present on that circuit board. This is another way that a small circuit board might look, and here these are the socket areas, or the areas in which the leads from the chips would be placed and then soldered in. This is called a printed circuit because all of these etchings started as a solid plate of copper on some plastic sort of a base and photographically exposed with a chemical that resists the etching of acid, so that when placed in an acid bath, only these parts of the original plate remain, forming conductors as well as the physical means by which a chip is attached to this board. It's not really printed. That name applied years ago when people thought these things looked printed, but actually they're etched on plastic or other kind of insulating material in this pattern that represents the circuit. So once the components are placed in this board and fastened in and soldered in, the circuit is complete. And this is the motherboard here. It's placed within a computer's case. We have a power supply here, we have the disk drive here, and perhaps a CD-ROM drive, a lot of connecting cables, a fan to cool off the main chip, which might be this one here, this squarish looking chip. Because of the circuit components and the electricity going through them, a chip like this generates heat. It's unfortunate, but that heat is generated and wastes electrical energy, and in effect can damage the chip unless it's cooled down to some degree by a fan like this. More modern chips, by the way, work at a lower amount of energy, and therefore netbook computers or devices like the iTouch or the iPad don't have fans in them because they use smaller amounts of power. The heat generated isn't so great as to damage the circuitry, and it can be dissipated just by ordinary contact with components and the air circulating around a device.